Hello students, welcome back. In this video we are going to continue with Chapter 7, Estimating Parameters and Determining Sample Sizes. Section 7.2 covers Estimating a Population Mean. Our last video covered Section 7.1, Estimating a Population Proportion. Now we're going to do a mean. So the main concept here is that we are going to present methods for using a sample mean, x bar, to make an inference about the value of the corresponding population mean, mu. In plain English, we are taking a sample, we are getting the mean of that sample, and we are trying to figure out what conclusions can we make with a confidence interval about the mean of the overall population. Our last video, for example, we said, okay, let's take 100 M&Ms, and if 21 of them are yellow, can we say that 21% of the population is yellow? And the answer was, no, you can't, but you can use that 21% as a starting point to make an inference about the overall population probability. So now we're going to be talking about mean, x bar. Okay, the three main concepts are the point estimate, which is that the sample mean is the best estimate, or the best guess, if you would, about what the overall population mean is. So the sample mean is your starting point for what the population mean is. Again, confidence interval is using sample data to construct and interpret a confidence interval estimate of the true value. Remember, you got to know the difference between x bar, which is sample, and then mu, which is population. Finally, sample size is the sample size necessary to estimate a population mean. So confidence interval for estimating a population mean with sigma not known. So we are going to construct a confidence interval used to estimate a population mean. Here are your symbols. We should know by now that the mu is the population mean, x bar is the sample mean, n is the number of sample values, capital E is margin of error, and lowercase s is the sample standard deviation. So some requirements. In order for this method to be valid, in order for us to be able to have this work, you have to meet two requirements. One, the sample is a simple random sample, talking about biases and getting good quality data. It needs to be simple, random. And number two, really the more tangible one in terms of data values, is that you need to have the population must be normally distributed and or n is greater than 30. And if it's not normally distributed and n is still greater than 30, we are protected by the central value that we covered in, I believe that was section 6.4 for that, the central limit theorem. Okay, so in order to do that, we are now doing what is called a t-distribution. Up until this point, we've done z distributions, but now we're doing a t-distribution. And this was formulated in 1908 by William Gossett, statistician who worked for Guinness Breweries, also known as the Guinness Book of World Records Company. And we are using table A3 in your book. Remember, the z distribution was A2. Now we are doing table A3 for t distributions. Another thing to note is that William Gossett, when he was doing his work, he went under the pseudonym student. So sometimes you'll see t distribution being called a student t distribution. That would be why. So using the t distribution table in your book. The table gives values of t based on degrees of freedom. Now, degrees of freedom are they're related to how many samples you have, so your sample size. And it is arranged by confidence levels. If you're looking at it, you look at the top, it will tell you what percentage it is based on what your alpha will be. So degrees of freedom is going to be n minus 1. So if you have 40 as your sample size, n is 40, your degrees of freedom will be 39, n minus 1. And then if you look at your column and your rows, you find that the degrees of freedom goes up 1, 2, 3, 4, 5, all the way up through 40. And once you get up to 40, they start going by intervals of 5. It goes 40, 45, 50, and so on. So for when the degrees of freedom is greater than 40, the real value would be somewhere in between the, say, 40 and 45, but we will always round down to the lower degrees of freedom in that case. So if your n was, say, 43, your degrees of freedom would be 42, which means that you would round down to 40. And you don't use rounding as if it was 43, you would not round up to 45. If it was 43 for degrees of freedom, you would still round down to 40. So here are some examples. Say you have and I encourage you to pull out your textbook and follow along with, just to make sure that you understand how to use that t-value table properly. We're looking at table A3 in your textbook. So say the value of n was 20. N minus 1 would give a degrees of freedom of 19. And say we were interested in a confidence level of 95%. So the area in the two tails would be 0.05, and then you kind of see where that corresponds. You get a t-value of 2.093. Another example, value of n is 15, n minus 1, degrees of freedom is 14, confidence level is 99%, so the area would be 0.01, t-value 2.977. Then if we had value of n is 35, degrees of freedom would be 1 less than that, so 34. And if we had a 90% confidence level, the area would be 0.1. Looking at where those two values would correspond would give a t-value of 1.691. And then finally, just to change it up a bit, now we're looking at degrees of freedom greater than 40. So if n was 104, the degrees of freedom would be 103. So we would round that down to 100, and now we're looking at where 100 and 0.02 correspond, giving a t-value of 2.364. Okay, so what do we do with that t-value? So this is similar to the margin of error concept from section 7.1. So now we're going to create a confidence interval. So the margin of error formula would be margin of error equals tau of alpha divided by 2, which is what we just found using the chart before, these values over here, multiplied by the sample standard deviation divided by the square root of n, which is your sample size. So the confidence interval is associated with the confidence level, such as 0.95 or 95%, and alpha is the complement of the confidence interval. Okay, critical values is what we are using in our student t-distributions. That's what we calculated before, and we covered before that degrees of freedom is just going to be n minus 1. So some key points about the student t-distribution. If a population has a normal distribution, then the distribution of t equals the sample mean minus mu divided by s, sample standard deviation, divided by the square root of n. Complicated formula, but we're not actually going to be doing that by hand. We're going to be using the table A3 for all of that. Degrees of freedom we covered already, and we just really what you need to know about this is that the degrees of freedom is going to be n minus 1. We already covered how to find the critical value using A3, and technology can also be used. We're actually going to cover how to find that using the calculator in this video, and also you can find a link on the module for you to be able to determine tau using StatDisk and StatCrunch. Okay, the student t-distribution is different for different sample sizes. The student t-distribution has the same general shape and symmetry as a standard normal distribution, but it has greater variability that is expected with smaller samples. Basically, the smaller the sample, the less normal it will be. And as n increases, you get more and more of a ideal standard normal distribution. So the student t-distribution has the same general symmetric bell shape, but it has more variability. And then as n increases, so does the shape becomes more and more standard. The mean of a student t distribution is t equals 0, just as the standard normal distribution has a mean z equals 0. So that midpoint right here where the peak is going to be t equals 0. And the standard deviation of the student t distribution varies with the sample size, but it is greater than 1. Unlike the standard normal distribution, which you guys should know has s equals 1. And again, as the sample size gets larger, the student t distribution gets closer to the standard normal distribution. Okay, let's now focus on how to actually solve problems with it. If you're like me, a lot of the background stuff is good to know, but it doesn't fully make sense. You can't fully wrap your head around it until we do some examples with it. So let's talk about the procedure for constructing a confidence interval for the population mean, mu. So 1, verify that the 2 requirements are satisfied. The 2 requirements we did on the slide, I'm not going to be able to find it now. Of course not. Here we go, this slide. Sorry for the jumping around. The sample is a simple random sample, and it must be normally distributed and or n is greater than 30. Okay, and then with sigma unknown, as is usually the case, we use n-1 degrees of freedom and technology or table A3 to find the critical values. Once we verify that we can use the t distribution, we then find out the critical values using the table. Once we find the critical value using the table, we can evaluate the margin of error using this formula right here. We plug in the value from the table in for tau of alpha divided by 2 right here, multiplied by s divided by the square root of n. Once you get the margin of error, now we can use the confidence interval, same way we did last time. So you can write it in 3 different ways. You can write the sample mean minus margin of error is less than the actual population mean, which is less than the sample mean plus the margin of error. Or you can write it as sample mean x bar plus or minus margin of error, or you can write it as a interval notation right here. And with an original set of data values, round the confidence interval limit to 1 more decimal place than is used for the set of data. So let's do an example. Finding a critical value tau alpha by 2. So find the critical value corresponding to a 95% confidence level given the sample size n equals 15. Well, we're going to assume that the requirements are met. We're not going to try and trick you with that, at least not without giving you proper ways for you to determine if it wasn't. So if nothing's given, assume that those requirements are met. So because n is equal to 15, the number of degrees of freedom is n-1, which is 14. You got to know how to use your table. So the 95% confidence level corresponds to alpha is 0.05, giving an area of 0.025 in each of the 2 tails of the t distribution as shown. So 95% means from here to here, this area is 95%, meaning there's 5% left over. Divide that by 2. There's 2.5% of the total value here and 2.5% of the value here. Then we have that using your table A3, you get a tau value of 2.145. You can also use technology to find that, which we were going to do an example later, which we will do it both with the table and with the calculator. So again, tau is 2.145. Once we have tau, so solution would be to find the critical values. Use the column with 0.05 for the area in 2 tails, or use the same column with 0.025 for the area in 1 tail. The number of degrees of freedom is degrees of freedom equals n-1, which is 14. We get the critical value to be 2.145. Did that problem not ask us to get oh no, this problem only asks to get the critical values. We didn't actually have to get the confidence interval. That was my reason for hesitation. So sorry about that, but yes, now we know how to get the tau value. The next example will cover actually finding a confidence interval. That was just practice getting the critical values. Finding a point estimate and margin of error from a confidence interval, sometimes you'll be asked to find different things. So perhaps you know a confidence interval and you want to figure out some point estimates and margin of error from that. And here are your two formulas for that, very similar to what we did in section 7.1. So here are your two formulas for that. This table just kind of gives you an appropriate distribution to use given different conditions and circumstances. So if the sigma is not known and normally distributed population, or sigma not known and is greater than 30, use the t distribution. If sigma is known and normally distributed, or sigma is known and n is greater than 30, use a normal distribution, the z-tables. And if population is not normally distributed and n is less than 30, you can't use either of these methods. You have to use another method, which is section 7.4. So here's the meat and potato example. So if you're going to really focus on any example in this lesson, focus on this example. A sample of 6 adult elephants had an average weight of 12,200 pounds with a standard deviation of 200 pounds. So would that be a sample standard deviation or population? I would hope you would say sample. And this would be your X bar, because it's the mean of the sample. So assuming that the weights of adults are normally distributed, that tells us that we could use the t distribution. Find a 95% confidence interval. Okay. So again, first thing is you have to check the requirements. N is less than 30, but because it's normally distributed, we can use a t-table. Now we can go straight to the formula. Okay, we have margin of error equals the critical value times s divided by the square root of n. Using our table, we can figure out that the tau value is going to be 2.571. So we now have 0.05 and degrees of freedom of 5. You get your tau multiplied by your sample standard deviation is 200 divided by the square root of your sample size, which is 6. You get a margin of error of 210. So your 95% confidence interval is going to be the sample mean minus the margin of error, bounded by, on the right, the sample mean plus the margin of error. So we are saying that the population of all elephants, the population mean is going to be in between 11,990 and 12,410. We are 95% confidence the population mean falls within that lower bound and upper bound. Now checking using the TI. So on your calculator, press stats, go over to tests, and then keep going down, and then number 8 is going to be your t interval. Fill in the values. So go to stats. You have to make sure, I think the default is going to be data. Go right to go to stats. And then your X value, your X bar was going to be 12,200. Your sample standard deviation is going to be 200. Your N value is going to be 6. And your confidence level is going to be 0.95. If you were not given those values and you were just given a list of data values, you can use data, create a list, and then it will calculate these values for you. But once we have this plugged in, we can go over to calculate, highlight calculate, and hit enter. Computer or the calculator will take a minute, and then it will spit out this interval value, which is the same as what we got by hand. And that's it for this section, guys. Any questions, always email me. Thank you.